Hello everybody, my name is Brenton Adey. I'm a senior data analytics consultant at a company called Telstra Purple, all the way down in Western Australia, Perth. I'm also a tutor at the Data and Analytics Bootcamp for the University of Western Australia, and then lastly I'm a master's student at Deakin University for Applied Artificial Intelligence, although it's Applied Artificial Intelligence, probably a little bit different to what we're going to be talking about today. I think I've left it up there long enough. You've all seen the description, seen the title. You might be thinking, what is a PowerPoint AI? Surely it's just a trick, just a play on words to get you through those doors. And don't worry, we'll get to it, but there's something I just have to cover off first of all. This isn't a talk about PowerPoint. If you came in here hoping for the latest tips and tricks on how to create flashy slide decks, then one, I'm profoundly sorry, and two, it was in the talk description. Also, we're not going to be talking about any sort of practical ways to apply a PowerPoint AI. The output of this talk shouldn't be, hey, let's take all of my machine learning models and transfer them into PowerPoint. Would not recommend that. No, in this talk, we're going to be breaking down the fundamentals of artificial intelligence, specifically one avenue that we use to get to artificial intelligence, which is machine learning. We're going to find out the fundamental principles and then use that and PowerPoint as an illustrative tool to see how simple these algorithms really can be when they're broken down. So with that, as an exercise at the end, I'll leave it to you to think about how crazy I am or not. Unrelated, here's a picture of me as a robot. Somehow that seemed like the most fitting image to have of me. I've always been fixated on pushing the boundaries of a concept. When I was young, we had this science project where we had to build a car and propel it as far as we could, with the stipulation that we couldn't use a battery-powered motor. Most kids did some combination of an elastic band, maybe pushing it down a hill. I won by adding a solar panel power motor, with the fact that, yes, the sun's not really a battery, and if it is, with like conservation and energy, all of that, everything's using it just to varying degrees of inefficiency. The sun's not exactly a limited resource where I come from. And I never really grew out of this pushing the boundary of the concept. See, when I started learning about machine learning and AI, it was all under the disguise of big data and complex mathematics. And back in the day, this felt a little bit disingenuous. Smart people often like hiding really simple topics in complex jargon because it makes them feel better when smart people than them were trying to teach them in the same way. Fundamentally though, machine learning is actually pretty simple. The term AI floats around a lot these days, and it's usually as some ex machina style magic to solve all of the world's problems, which is great for me in my day job analyzing data as I get to run around pretending I'm some magician. But a magician never reveals his secrets. And today I'm hoping to take you behind the curtain and really see how simple machine learning and AI are, and how applicable they can be to so many different scenarios, even a PowerPoint. But, as some of you may be familiar, there's a topic that we can't not discuss when we're talking about machine learning, and that is maths. Grueling, repetitive, complex mathematics. That's right, NDC, I tricked you all into a 1-hour lecture on linear algebra and multivariate calculus. Who's excited? Except, we don't really need maths to talk about machine learning. Yes, it comes up a lot when we're trying to apply these things, but we don't need to use it to talk about the fundamental principles. As much as I would love to get into intricacies of stochastic gradient descent, cross-entropy loss between distributions, Q-learning, all of that fun stuff, those of you who just felt the blood drain from your face as the mere thought of maths can just relax a little bit. But if we're not going to talk about maths, then what are we going to talk about? Well, if you looked up the definition of machine learning in a little site I called Wikipedia, you would see this following definition. Machine learning algorithms build a model based on sample data, known as training data, in order to make predictions or decisions without being explicitly programmed to do so. That without being explicitly programmed to do so is quite important, so we'll keep it in the back of our minds, but this is wild, right? Creating a program that can think for itself, that can make predictions and decisions. Surely this is just a wild new innovation. Well, this is often talked about as the first instance of the use of machine learning, and it's attributed to Arthur Samuel in 1952. Arthur Samuel was a pioneer of machine learning for IBM, building computers to play checkers right back in 1949. Okay, but that's just one application. What about all these fancy new ChatGPT large language models? Computers that are built to try and mimic the human brain. That might be new, right? Well, here is a schematic for the Mark I perceptron. This was the initial machine learning algorithm used to mimic the workings of a human brain for computer vision in 1957. And though the technology has evolved and the applications have changed a little bit, this exact theory was used as the basis for the resurgence of neural networks in 1990s and then further forward to all of the autoencoders and deep neural networks that we see today. So before we go on, there's just a few things that I want to clarify. When we're talking about machine learning here today, machine learning is not only for big data. It's also not only for large-scale compute. And machine learning is not magic. Okay, well, that's a bit strange. That's what machine learning is not, but what is machine learning? And when I was thinking about this, I wanted to write a talk about how simple it was, just the basic fundamentals of the algorithms of machine learning. I was trying to think of a way that I could apply it. Some environment that was so dead simple, so restrictive that I couldn't possibly hide behind any of my toolings or my great mathematical skills. I think this might do the job. Machine learning is about a way of constructing a model that describes things about the real world without us having to describe every single detail to it. In a way, it's about transferring knowledge from some known quantity to a known quantity. And we do this sort of learning all the time in our real lives. When I was a kid, I spent a lot of time learning the guitar. Probably too much time. I should have spent more time on my hair, maybe. That was right up until high school, when there was an audition for a high school musical band, and there was about maybe 5 or 6 people lining up for the guitar part, but no one lining up for bass. So I thought, what a golden opportunity. This is fantastic. I can immediately get a spot in the band. Does anyone here, do we have any bass converts from guitar? I can't. I see maybe some nodding. I thought, super easy. They've got strings, they've got frets. Well, I'm afraid to say that my first audition absolutely bombed. So it was only after successive iterations of practicing, admittedly failing, getting it wrong, and practicing, that I was able to transfer the knowledge that I had learned from my guitar playing into the bass. Machine learning algorithms are very similar. They go through this successive iteration process by trying to learn some known quantity, some unknown quantity from a known quantity. Let's put it maybe a different way. Let's assume we have a group of people, much like yourselves, tasked with predicting the result of a coin flip. And let's say for every correct guess you get a cookie, and that's just to prevent anyone not taking this very serious experiment seriously. Without any prior knowledge, except for the fact that maybe a coin has 2 sides, I think we can all agree that within a certain margin of error, we'd all expect the group to get about 50% of it right. So we start this experiment. 1 flip turns up heads. 2 flips, heads again. 3 flips, heads. What a coincidence, some might say, and others might start to catch on. 4 flips turns up heads. 5 flips, heads. The group is getting suspicious now. Cookies are flying left and right. Given enough time and enough successive iterations, people will learn about the coin's true nature. It's not an ordinary coin. The group started around here, randomly guessing 50%. But then eventually, with successive iterations of turning up heads and getting rewarded for getting it correctly, and that cookie getting ever more enticing, people start to learn that it's actually a double-sided coin. Now, importantly, The part about this process that makes it an iterative machine learning process is that no one ever told any extra information about the coin. It was inferred from the iterations of getting it wrong and getting it correctly and being rewarded as such. I want to dive into this process a little bit more. We're trying to break this down into its fundamental level so that we can apply it and use PowerPoint to illustrate this tool. So there's many different types of machine learning you might have heard of. Generally, we say that there's about 3 general archetypes. There's supervised, unsupervised, and reinforcement learning. But they all follow these same basic 3 steps. First of all, we need to create a test. What is the model trying to do? We need to define a way to score the test. How do we tell if the model is good or bad at what it's trying to do? We then, and most critically, need to create a way to punish or reward the model for the score that it just received. Now again, these 3 components are what we're going to use to build our AI out of PowerPoint. If we take these fundamental components of a machine learning algorithm by stripping away all the maths and complexity, that's how we're going to achieve our goal. The aim of machine learning, as I said, is to generate some generalizable model, something we can apply to never before seen data, or gain some insight about data that we do currently have, or generate adaptive behavior. Maybe that's the occurrence of a disease. Maybe it's grouping people in a way that sells the most t-shirts. Or maybe it's creating the best goddamn cat video of all time. These problems are vague, but humans learn to do it through years of medical study, years of user experience surveys, and years of computer science study, respectively. In machine learning, we look for the answer in the data that we have by following these 3 steps: test, score, and punish and reward, much like a student would prepare for an exam. So indulge me for a second while we take a stroll down metaphor lane. We're going to open up Brenton School of Machine Learning Studies. In this school, we have students working day in, day out to produce results. In this metaphor, our school is the model, and our students are just instances of training a model. They're one guess of the coin flip. To get this school to learn and perform in some of the top schools, we first need to define a test. We need to find a way to get a standardized measure of comparing from one school to another. After we define this test, we need to know how good or bad the school is performing. We need to find a way, what is a good score? What is a bad score? What will end in us losing our funding and turning off the lights forever? When we give this test to each individual student, to each individual iteration, we then need to have a feedback loop. We need to reward students who are getting a good score and punish those students that are getting a bad score by whatever means necessary. And then we give this test over and over again. Hopefully, the students will be getting better if they're rewarded for doing their test well and punished for doing badly, maybe not studying quite as hard. It's important to note that we're controlling the students within the school. There's no way to reward or punish the school as a whole. It's the students that are learning. Anyone that's tried to control any group of students or children will know that it's just chaos to try and control them all at once. This is the same for machine learning. We really only have control over the individual iterations at the score that it just received, not as a whole. An alternative way you might want to solve this problem is by getting students to memorize the answer to the test every single time. And although, yeah, this would work, I don't know about you, but I definitely can't memorize a whole entire test. And let's say the curriculum changes. All of a sudden, our students are worthless, or, in the guise of our school, because they can't answer the questions that they didn't memorize. Let's take a step back from metaphor lane. Not everyone enjoys that. We'll talk about a real-world example. Here is a picture of some samples from the MENACE dataset. It's pretty simple. It's often called the hello world of computer vision. In it, we have 70,000 labeled handwritten digits. In this case, our test is really clearly defined. We need to create a model that can predict an unseen handwritten digit as 0 through to 9. So we'll take a first pass iteration. This is about the simplest model you can get, just a random guess. We'll generate a number between 0 and 9 and assign the output of our model to be that. We can test this quite easily. In fact, if we did, we'd see that it's about 10% accurate. This is much less like guessing 50-50 on a coin toss. However, we have no way to change the model's behavior. It will always get 10% accurate, no matter if it gets it wrong or right. So, let's try again. Let's define a model based on how dark the image is. It might seem strange at first, but for example, we might assume that a picture of an 8 will be slightly more dark than a picture of a 2, which in turn might be slightly more dark than an image of a 1. This is because there's more ink involved in drawing the digit of an 8 than there is a 1, so we might be able to define a model like that. In practice, a model like this gets around 22% accurate at its best case, which is twice as good as just randomly guessing, but it's still 1 in 4, 1 in 5 times that it gets it wrong. And critically, just like the model previously, we have no way of altering the model's behavior when it gets things right or wrong. The model's accuracy will stay at 22% no matter what we do. We can do better than that. Let's have a look at an actual machine learning model. Break down its components, see how it's using these 3 elements to generate a model that is much better. The following is an extract that I've taken from a book that I dearly love called Deep Learning in Neural Networks by Michael Nielsen. Don't bother trying to read the code. Importantly, I'm going to highlight one thing that other 2 models didn't have. And that's a way to reward good test scores and punish bad ones. For those interested, this is an example of a feed-forward backpropagation neural network. It simply just takes the output of a cost function and then uses a process known as stochastic gradient descent to apply a gradient. And it's really quite simple because you just do the chain rule to find the gradient at a particular point, except I did promise no maths. Nevertheless, this model is a machine learning model because it has those 3 components. It has a test, is the predicted digit equal to the actual labeled digit. It has a way of determining a good or bad score. That's the cost function that I mentioned. And it has a way of altering the model based on the score that it just received, stochastic gradient descent. That's just one example though. What about applying it to other situations? I sort of said that MENACE was a very simple model. It's like the hello world of computer vision, if you will. In it, we had a very clear labeled objective. If our model didn't predict the right label for a handwritten digit, then it's just not up to scratch. The interesting examples in the industry are when the test isn't so clear and how to provide a score is just as equally vague. So what about another time? This is a paper that I came across a few months ago, Onsets and Frames Dual Objective Piano Transcription. The goal that the authors of this paper were trying to achieve was transcribing an audio recording of a piano into written manuscript, something that someone would conceivably sight read and play the same music. This is full of fun maths and data science jargon, but the point of interest here is when the authors were trying to describe how they fixed the model's way of testing velocity. As they state, it's a pretty hard nut to crack. Sure, you can tell if a note written on paper is the same that was the note that was played. You can even test whether the transcribed note falls on the same beat. These are all numerical quantities of the music that are easily encoded. But how do you capture dynamics, volume, and expression? A note pitch is a note pitch, but what reference does a note's loudness have? Who's to say the recording isn't just loud or that there's so much background noise suddenly? Additionally, how do you correct the prediction of a dynamic when the context that it appears in is arguably more important? The emotional and cultural context of music in a sequence of soft notes and then a really loud note, or then a sequence of really loud notes, really differs when we're trying to transcribe what music is. The author, I love academic papers, they're kind of hand-wavy at this point, so they've discovered a never-before-seen method to truly test whether their model perfectly transcribes the dynamics of the player. However, what's important to note is all that's been done is some math magic to calculate the score based on the average volume of the recording. They didn't discover any intrinsic property of music or dynamics that was easily encoded. They simply defined a test. The test could have easily been all notes are piano if they're negative 5 decibels, and then it would have been really good at generating a transcription where every note that was negative 5 decibels is transcribed as piano. So that's when the test is a little bit more vague, but what about the score? Because I sort of glossed over that a little bit before. I said the score was just some aggregation of the student's scores. So let's take a step back and be a little bit more rigorous, because I'm deeming you all mathematicians now. A score is a number that we try to capture how good our model is. Let's say, for example, you were trying to classify cyber attacks, which is exactly what this paper was trying to do. I don't know if I have to reiterate this, but cyber attacks are bad. We don't want them. To protect ourselves, we want to wade through incoming traffic in a system known as an IDS or an IPS. But hiring a grad to do this is probably inhumane, maybe a little bit impractical, so instead you might hire a grad to generate a model to classify these instances instead. In this portion of the paper, there are 5 types of attacks that are described. Your first thought on how to calculate the performance of a model might be to count how many it got right and then divide by the total number of points. In this, you'd be talking about accuracy, which is a very common metric for talking about the performance of a model. It's often the one that I get non-technical stakeholders talking to me about. We need to optimize for accuracy. Except, let's say, for example, I had a specific instance of traffic coming in and out of my system. Attacks are quite uncommon, really, in reality, to normal traffic. For the sake of argument, maybe I have 500 instances of normal traffic, 20 denial of service attacks, 10 probing, and then 5 of the other 2. I can have a model that just predicts every traffic as normal. And technically, I'd get an accuracy of 93%. But I'm just letting every piece of traffic go by. Yes, it's accurate. I'd be happy with a 93% score, but it's clearly not performant. So accuracy is what we say not robust to this class imbalance. Also, there may be repercussions on labeling something that isn't an attack, what we would call a false positive, or labeling something that isn't an attack as normal, a false negative. In this case, it's pretty bad to let an attack go through, but mislabeling normal traffic can usually just be sent to our Security Operations Center to deal with. Of course, this is very domain specific. In healthcare, we have this really interesting trade-off between sensitivity and specificity. We don't want to miss people with an illness, but we also don't want people going through potentially invasive and unnecessary treatments because our model incorrectly assigned them to have an illness. Instead, in classification, we use other scores such as recall. What proportion of the attacks that we got right were actually attacks? And what precision? What proportion of the traffic that were attacks did we correctly identify as attacks? Back to the paper, you can see a huge difference in the model's reported accuracy and their precision and recall. In this, when we're defining our score, we have to think about what's really important. Is it how many we got right, or is it that we're actually assigning the attacks correctly? Now, there are plenty of other types of scores, not just for classification. An interesting one that you might come across for stuff like the large language models are the BLUE score, which is trying to contain syntactical and semantic information between 2 sentences and compare them between each other. The important thing to note, though, is that every score is trying to encapsulate the whole performance of a model down to a single bite-sized chunk. So there's bound to be some sort of trade-offs. Regardless of how you phrase it or how you put it, the machine learning process is comprised of these 3 basic steps: test, score, punish or reward, and repeat. And we're going to use this very shortly. But let's just take a breather. That was a lot. And I did promise something at the beginning of this talk, so we should really get into this. Machine learning can be used in all applications. I hope that's clear by now. It's more than just classification regression. It's more than just throwing some data at a big scale compute and doing some fancy linear algebra on it. As long as we use those 3 steps, we can apply it in any different scenario. And that's where this comes in. Training an AI to play Tic Tac Toe. Except, I'm not sure that that would be good enough, right? Who's to say that I didn't just pull out the usual tools I'd use to code up an AI, that I'm not using smoke and mirrors, that I'm actually doing all the complex mathematics and not showing you? No, I need something that's so simple that you'll believe me that machine learning is just these 3 steps. I think this will do it. Okay, very quickly, for those who need a refresher, Tic-Tac-Toe, or Noughts and Crosses, as I've heard it being called in other places, not Australia, is a 2-player game played on a 3x3 grid. Each player is assigned to be either a cross or a nought, or a circle. And each turn, they place where they want their symbol to be on the 3x3 grid. The winner is the person to get the first person to get 3 in a row. If no one gets 3 in a row, then it's considered a draw. It's no chess, but I like to think it's the simplicity that gives it its charm. Secondly, in true consultant fashion, I'm going to really caveat this and define the scope of what we're working with. The aim of this game is to demonstrate how simple machine learning is, once it's stripped away from all that mathematics that we talked about. So, no code is allowed. Now, full disclosure, there were some macros involved. As you'll soon see, to get this working involved many slides and many animations. So to save myself an eternity, I hacked away some old VBA scripts to automate the insertion of animations and slides. We will not be using this in the process to train our model. That's surprising to some people. When they saw PowerPoint AI, they immediately think I'm, doing some machine learning in VBA. No one wants to do that. Even me, a sadistic person, to build a PowerPoint AI isn't going to build VBA. In addition, for the game theorists out there, depending on how you define a game, there's about 255,168 possible games of tic-tac-toe. We want to reduce this a little bit, so for the point of a demonstration, I've reduced this down to, does the AI win in the first 3 moves? Now, this might seem like quite a radical simplification, but in reality, a lot of the games where a player doesn't win in the first 3 moves, a majority of them end in a draw. So we're not losing that much information for the end states. In addition, the AI will always make the first move. Tic-Tac-Toe is a really interesting game of a biased game where the person who moves first has a different game in different optimal turns to if the person who goes second. So we're going to be confining ourselves to that first part. In addition, we'll utilize reflective symmetry and rotational symmetry to try and reduce the number of turns that the AI could possibly make. What do I mean by that? Well, in this example, there are 5 blank spots in the board. This means that potentially the AI could move to 5 different locations. Except in reality, the AI is only ever going to move to 3. This is because the other 2 on the right-hand side are just reflectively symmetric of the other states. The human players won't have any such restrictions. We'll be allowed to place a nought wherever we want. I guess important to note here, I defined the AI to be a cross and the human player to be a nought. I don't know, that just felt right. I just got the vibe, but come complain to me if you think that's wrong. I'll talk a little bit about the inspiration, the people who cursed me on this venture. The first is the work of mathematician and comedian, because there are some of us who are funny, by the name of Matthew Parker, who ran a project training a machine learning algorithm to play tic-tac-toe with matchboxes. This was based off Donald Michie's work MENACE from 1961. Michie's model was made of 304 matchboxes, where each matchbox represents a single state of the board. And you might ask, why only 303? Why not the 1,830 or something? Well, Michie only had to worry about the AI moves for one. He had access to the physical person that was doing the other moves. And also, he didn't track the steps taken to get to each individual state, because he used some archaic tool to track that. There's a pencil in a paper? Yeah, I've never heard of it. In Mickey's work, each matchbox had a set of coloured beads, and these coloured beads represented the chance to move to a particular location in the board. When it came time for the AI to move, an unbiased operator would close their eyes and pull out a coloured bead. Say, for example, they pulled out a red bead. This would indicate that the AI is going to move to the right-hand side. Alternatively, let's say the operator pulls out a green bead. That would mean that the AI would move to the centre square. The theory here is that the more of a particular colour bead, the more likely it is for the operator to pull out that bead, and it's more likely for the AI to make a move when it's in that state. When the AI played a game, each time it won the game, the operator would then go ahead and place a coloured bead associated with the state that was next to it to increase the chance that it's going to move to that winning state. Conversely, if the AI lost, then they would take out a coloured bead, which would reduce the chance that it's going to make the same mistake again. Then, they would do again and again the same repetitive process. What results from this is a set of 304 matchboxes that practically only contain beads that move the AI into winning or neutral positions. Mickey's work is one of the first instances of what we now call reinforcement learning. Okay, the second inspiration I got from this is Tom Wiederhain's talk, Great Impractical Ideas of Computer Science, PowerPoint Programming. Fantastic talk. It really opened up my eyes to the programming potential of PowerPoint. Programming potential of PowerPoint. So PowerPoint then, like, what is this? I've heard from the streets, some people don't think that it's the greatest tool ever invented, and they're of course wrong, because PowerPoint has everything that you could possibly want. It has text, it has shapes, but most importantly, it has animations. Now, you might think this is silly, all these shapes and funny things, but the shapes and animations are the key to what allow us to build a machine learning model, because they allow us to do something that developers take for granted every day: state management. In our model, each slide will represent a turn from either the player or the AI. We will then use shapes and animations to store the state and help the machine learning algorithm learn. So for those playing along, there's 1,830 states, which means a PowerPoint slide deck with 1,830 slides. Each slide state consists of the following: the board. This one's pretty simple. It's just the number of noughts and crosses and their location on the board. Interestingly, as part of the state, we also store the previous steps that it took to get to that state. We'll talk about why in a second, but we do this using one of my favorite PowerPoint features, zoom transitions. So that's what the state consists of. We have the current location of all the noughts and crosses on the board, and then the steps that it took to get to that current state. But how do we move from one state to another? Well, there are two types of turns. There's a player's turn and an AI's turn. In the player's turn, it's pretty simple. There's actually a collection of invisible shapes here. They have no fill, they have no outline, but what they do have is a hyperlink. And that hyperlink for each shape just corresponds to the slide where the nought just so happens to be in that particular location. So there are 8 different places that are blank here that the player could potentially move to. That means there's 8 just invisible shapes having a hyperlink. When a user clicks on that, unbeknownst to them, they're navigated to a slide that just so happens to have the nought in the location that they clicked. Things get a little bit more interesting for the AI. To be sure, a human player still has to click for the AI. I'm not building a PowerPoint AI to control a mouse just yet, but please don't give me any crazy ideas. This is just like the operator pulling out a colored bead from a matchbox. Just like the human player, the AI's turn has a collection of invisible shapes. The difference here is that we're utilizing the blink animation so that each one of these shapes is randomly blinking. Another difference is they're all in the same location, just under that click to make AI move. Only one box is clickable at a given time, but it still represents a chance to navigate to another portion of the board. To show you a demonstrate of how this is working, this is what it might look like, except in reality, those shapes are blinking a lot faster, there's a lot more of them, and they're all under the same location under the click to AI move. But they have a hyperlink to a particular location of the slide. When you initialize this model, you create an equal number of shapes that represent an equal chance for the AI to move to every location available to it on the board. What does that mean? Well, there's 7 different locations that the AI could move here because there's no reflective or rotational symmetry. That's 7 initialized with 10, 7 times 10, 70 randomly blinking shapes for each state in this slide. 7 times 10 times 1,830. I'll leave it as an exercise to figure out how many shapes that is. But how do we train? How do we confirm that what we've just created is indeed an avenue that we can use to train a PowerPoint AI to play Tic Tac Toe? Well, to do that, we have to look at these 3 components that I kept hammering on about the earlier part of this talk. To talk about how we defined our test, how we're going to score it, and then finally, how we're going to provide punishment and reward for each iteration of the game. So, due to the limited capacity of a lone man's calendar and the sheer number of games of tic-tac-toe, we've reduced the test to, does the AI win in 3 moves? This is equivalent to the logical converse, does the AI lose in 3 moves? But I like to be optimistic. The score is, there's 3 different outcomes. This is because the number of winning games isn't evenly distributed between the total number of games in tic-tac-toe. By that I mean there's far more games in tic-tac-toe that end in neither the player nor the AI winning. So we have pass, the AI wins, neutral, neither the player or the AI wins, and then fail. The punish and reward is kind of fun. This is why we had to have that crazy setup of randomly blinking shapes. Because when it passes, we want to increase the chance that it's going to move to those particular states. We do that by increasing those number of blinking shapes that correspond to the place in the board that makes the AI win. Neutral will just, nothing happens, we'll just run the test again. As I said, there's a lot more games that end in neutral, so if we tried to do anything fun with that, model would just converge right down into whatever the neutral state was. And then lastly, fail. We're just going to try and reduce the chance that it's going to make mistakes by deleting the shapes that represent moving to those particular locations. So here's an example. Again, we've initialized the model with 10 random blinking shapes for each single one. And these shapes represent the probability that the AI is going to move to the future state. If there's 12 random blinking shapes to correspond to one of the states, that means it's more likely that when the player just so happens to click on that button, that it's going to be front and center due to the blinking animation, and it's going to navigate there. And we run a test, a training epoch, if you like. Let's say the AI wins. This represents the best possible chance. At some point, the player must have made a mistake, or the AI had a chance to move, a chance to win, and it took it. We want to encourage this from happening as much as possible. When the AI is at a similar position, we want to have the maximum likelihood that it's going to make the same decisions and lead to a winning state. So, we backpropagate using those fancy zoom transitions through every single one of the previous states and increase the chances that it's going to make the same decisions again. Conversely, let's say we run another test. This time, the AI loses. At some point, maybe it had a chance to win and then it just ignored it, or maybe the player got lucky. In either case, we want to discourage this from happening. We know that these sequence of events lead to a losing state, so we take those chances away. We make sure that when it's in the same state again, that it's not going to end up in that losing state by deleting the navigation shapes. Eventually, we might expect there to be no navigation shapes that represent this sequence of events. So let's look at it in action. This isn't on this slide deck, by the way, because I think my computer would explode if I had 1,830 slides also on this deck. And this is a recording of the actual slide deck. So we see the AI makes a few moves, and then the player makes a mistake here. The AI has a chance to win, except it's never seen this state before, so it just makes a random guess. We want to discourage this from happening. We don't want it to move down when it's in a similar state. We ideally want it to move up. So we backpropagate through every single one of these states and delete the chances that it's going to move the state future. That way, when it's in a similar state, it's less likely to go down to the bottom, and it's more of a chance to win at the top. And then we do it again. Again, the AI makes the first move. This time the player makes a different move. The AI goes in the center. I think that's a pretty good play for the AI, but the player is smart this time. It defends, setting itself up to win. Now, an optimized AI would only have navigational shapes that let it go down to the bottom, except it hasn't seen this state before. So it goes to the top right-hand corner, letting the player win. And we want to discourage this from happening. So we backpropagate, copy and paste the shapes, and do it all over again. In order to do this, we need to run a lot of iterations because we need it to be able to see all of the states that it has been in. I have had some questions in the past about how is this actually working, because I promised that there was no code involved. Well, I'll take you through step by step. This is an example of a state in which the AI won. We see it's got 3 in a row. We want to encourage, when it's at the very first state, to follow these sequence of events to get to where it is today. So we use control-click with a zoom animation. We end up into the state that it was at previously. Then we find all the shapes that are indexed with 3. Why 3? Because 1, 2, 3. We know that that third one is a state that wins. This is why I had those VBA scripts to automate the insertion of the shapes, because they're all named indexed to where the location of the board that it is. We find those, and then we do every developer's favorite tool, copy and paste. What we then do is navigate to the state that it was in previous to that, and do it all over again. And that's it. After successive iterations, we get a test, we score it, and then we provide punishment and reward. We've just successfully built a machine learning model out of PowerPoint using nothing but slides, animations, and shapes. But there's probably a question that you're all asking in the back of your mind, maybe throughout this whole talk. Why? Why does a fundamental understanding of machine learning matter? Besides for knowledge's sake, I guess. Well, clear now, I hope, is the distinction between traditional control flow logic and the machine learning approach. The difference suggests a fundamental change in how we conduct analytics, build automation, and start integrating this stuff into our business processes. In the other models we saw, like predicting a digit based on the darkness or just randomly guessing some things, these are examples of traditional control logic. If this, then that. Machine learning, if nothing else, is a tool that allows to move past this constrained test. It's not possible to know every if this, and it's certainly too time-consuming to label every then that. Machine learning allows us to tackle problems that we couldn't possibly know how to tackle beforehand. Not just predicting digits or analyzing text sentiment, but any process in which we can define a test, score it, and provide punishment or reward. All of the maths and code that machine learning developers build under the hood are just extensions that allow us to do this in different particular ways with the tools we have available to us. In the PowerPoint example, it was about how can we use shapes and animations to punish or reward a model for winning in Tic Tac Toe. In maybe something like IoT or compute at the edge, where we don't have all of the compute resources to throw at it. It's about how utilizing the tools that we have available to us to build these algorithms. For I mentioned cross entropy loss beforehand a bit facetiously. It sounds fancy, but all it is just a way to provide a score for a list of numbers and figure out how different it is to another list of numbers. Sometimes, though, it's not as clear, like with the audio transcription or the cyber attacks, about how we define our score and how we test it. When we're building an AI out of PowerPoint, it's not about trying to replicate and implement the complex mathematics in the background. It's about using the tools we have available to us. And this is where we enter the humble data scientist. It's a data scientist's job to experiment with these components. And different models come with different ways that you can punish or reward or define scores. from our humble PowerPoint, it might be asking, is there a way that we can reduce the number of slides? Or is there a different way that we can increase the chance that it's going to move to a particular state? Not all models follow this reinforcement learning approach, but the principles remain the same. For clustering, for example, let's say I'm trying to group a bunch of people. How can I tell that the group I've just created is the best possible group with only the information I have with the individuals at hand? Maybe you're building a classification model for building targeted ads. Do I really care about the fine details of what the customer I've classified as? Or do I just want a scattergun approach of every customer that I want to get targeted? Following from this sort of experimentation, a data scientist also does hyperparameter tuning. It's not something I really talked about in this talk, but hyperparameters are things we can configure that change the model's behavior that it can't immediately learn from the data. In the PowerPoint example, it might be changing the number of initial randomly blinking shapes for the AI, or altering how many we give and take away depending on the output of the score. In the end, machine learning taps into something that we take for granted every day. It's our ability to learn by repetitively doing tasks. Now, if you're interested in a follow-up, I've got some nice resources that I mentioned throughout this talk. I've said neural networks and deep learning. This is a fantastic book that similarly breaks down the fundamentals of what neural networks and deep learning are in this really kind of cool way. It is kind of maths heavy if you got excited about all the mentions of maths in this talk. On set and frames, your objective piano transcription. I was being maybe a little bit facetious when I was talking about it. So it was done by some colleagues, or like some people in Microsoft as well as some others. Really cool stuff. There's a lot of interesting applications for machine learning that fascinate me that are more than just the large language models, text generation that you see in the news that have got all the hype. MENACE, the pile of matchboxes which can learn, is the application of Donald Michie's work by Matt Parker. Really fun, really cool stuff. And lastly, great impractical ideas of computer science, PowerPoint programming. If you take nothing else from this talk, just investigate some of the cool features that PowerPoint has. The morph transition I've been using throughout this presentation, fantastic. I don't know who's developing PowerPoint, but if I could meet them, I'd give them a really big hug. I'd also like to thank all of the sponsors of NDC and NDC itself. This is always great fun, and I love talking about all this crazy stuff that I can do in my free time. If you want to reach out to me, either come talk to me. I'll be here for the party in tomorrow, and then for time immemorial, I hope. My Twitter handle is there for the people still on Twitter. LinkedIn is probably the best place to find me, and also got a little blog site that I randomly ramble about my different data escapades. But other than that, thank you very much.